Cauchy not only left us with a theorem, he also left us with a formula. So what are the ingredients of the formula? So again, we have a contour, arbitrarily shaped, potato shaped if you want. And then we have a function, f of z, which is holomorphic / analytic inside the contour. So inside it's holomorphic. And then a final ingredient is some internal point z0 inside the contour. And then Cauchy's formula basically allows us to calculate the value of f at that internal point based on a contour integral. Namely, the result will be f of z is 1 over 2 pi j, the contour integral of f of z divided by z minus z0 dz. So this is the famous Cauchy's formula. Before we go and try and prove this thing, a very important remark. Why is it so important that z0 is a point lying inside the contour? So pause the video and think about what would happen if z0 were a point outside the contour. What would then happen to this integral? So think about this for a while. So where is our integrand non-analytic? Now f of z by itself is analytic, so that's very nicely well behaved. But of course, things go wrong at the point z0 because there this function blows up, right? Now, in case z0 is lying outside the contour, that means that the problematic point is over here, and everywhere inside the contour, the function is nicely well behaved because there's only a single problem point and we've moved that outside of the contour. Now, if that's the case, then we can fall back on Cauchy's theorem, which basically tells you that a contour integral over a function which is holomorphic, so a closed contour integral, that in that case the result will be 0. So therefore, it's important that z0 is lying inside the contour, otherwise the result would be 0. Okay, with that out of the way, let's try and prove Cauchy's formula. It still would be useful to try and make use of Cauchy's theorem, but we can't because there's a problematic point inside. However, what we could do is try and do something clever by taking an extended contour. So the goal is to start from our original contour, okay? But rather than closing it like this, what we're going to do is we're going to make a deformation, first having a straight segment like this, then a small circle around the problematic point z0, and then we're going to close it like that. So this is our, let's say, our original contour C. This is a straight line segment L1, a straight line segment L2, and then a small internal contour, this little circle C2. Important to realize here is that now for this new extended contour, z0, the problematic point, is not lying inside the contour, but rather outside, because the inside, of course, is this region over here, and we've neatly sidestepped the problematic point z0. So now we have an extended contour, which we can use to apply the first thing, so basically Cauchy's theorem. Good. What we then going to do is taking the limits of this L1 and this L2 becoming infinitely close together, such that we can close this contour here and that we can recover in the limits our original outer contour. So what I suggest you do now is pause the video and try to apply Cauchy's theorem to this extended contour, split it up into its different contributions, and then see what happens if you take the limits of these two line segments becoming infinitely close together. What can you learn from that with respect to the calculation of the external original contour? Okay, pause the video and get to work. So the extended contour consists of 4 different parts basically, and we know that the sum of these 4 different parts will be 0 thanks to Cauchy's theorem. So the first part, the first contribution is our original contour C. I'm not yet closing it here with a little circle symbol because we're only going to close it if we take the limit of these things becoming infinitely close together. That's the first contribution. Then we have a contribution over the line segments L1. And then we have a contribution over our little circle here. little circle, which we call C2. Now, by convention, if we write an integral here over a certain contour, this means that we move through this contour in the counterclockwise direction. So that's just the convention, basically. Now, if you look very carefully about what happens here, once we reach the internal contour, we're actually going to traverse it in the clockwise direction. So if by convention this expression here means counterclockwise direction, since we now need clockwise direction, we need to have a minus sign in front of it. Again, nothing mysterious, it's just a convention, and we should respect that convention. And then the final part will be an integral over the line segment L2. And you've noticed I'm very lazy, I'm not writing all of the integrands here. But the end result is that they sum up to 0. So now what we're going to do is taking the limits of L1 and L2 becoming infinitely close together. This will result in the closing of the contours C and C2. And also, if you look at what happens here, once these things become infinitely close together, and thanks to the fact that our function here and our integrand is well behaved and therefore continuous, this will mean that an integral from here to here will be the opposite of the integral from there to there, and therefore L1 and L2 will cancel. And that allows us to write that the original non-extended integral that we're interested in, the integral of f of z divided by z minus z naught dz over c, is actually equal to a very similar integral with exactly the same integrands, z divided by z minus z naught dz, but this time over our contour C2. So the important part here is that C could have any funky shape, but C2 is one we choose ourselves, which is just a regular circle around the point z0. So this is the first thing we gained from this. We went from an unruly contour to a much better defined contour, which will lend itself much easier to, for example, parametrization. And that's the next step. Pause the video and parameterize this integral using the techniques we've seen before, and then take the limit of the radius of this little circle here going towards 0. And that should be sufficient to try and prove the theorem. Okay. So what's the parameterization we're going to use? So we need to parameterize a little circle around z0. So we're going to say that z on that contour is equal to z0 plus then a little circle r exponential j theta. And theta will run from 0 to 2 pi. Okay, so this is the parameterization we're going to use. And in this case, that means that we can rewrite our integral as an integral from 0 to 2 pi of f of z becoming f of z0 plus r exponential j theta. Z minus z0 becomes a bit simpler, becomes r exponential j theta. And then finally our dz becomes, so if we take the derivative here with respect to theta, that becomes j r exponential j theta d theta. And that's good news because this simplifies considerably. These things cancel. And finally, we just have an integral of j times the integral from 0 to 2 pi f of z0 plus r exponential j theta d theta. Now we're tantalizingly close to the end result. What we're going to do next is taking the limits of r going towards 0. And then we're going to assume that since we're dealing with well-behaved functions here, that we can exchange the order of the limiting operation and the integration operation, such that basically what happens here, if we take then the limits of r going towards 0, this thing becomes a constant. So the integrand becomes a constant. Does no longer depend on theta in the limit of r going towards 0. And therefore, we can just move it outside of the integral. So we just have j f of z0 times the integral from 0 to 2 pi of d theta, which is a fiendishly difficult integral. So that's just j 2 pi f of z0, which is indeed what we were after. So this is how we prove Cauchy's formula. Before we wrap up here, I want to draw your attention to the fact that this is actually a pretty spectacular result, because it basically tells you that if you have a function, and the only things you know about this function is that A, it's analytic, and B, you know the values somewhere on a contour, then automatically you will also be able to know all of the values of the function inside the contour. So very strange, a holomorphic function is able to extend itself based from values in a contour here to points inside that contour. So that's quite remarkable that a holomorphic function is able to do that.